Okay. Okay, so now let's see vectors in 2D. Okay, this is exactly what we are going to be looking at throughout this lesson for today. Not an easy to teach topic, but trust me, I am definitely going to do my best to a point whereby you can actually make sure that all that is written here makes sense. Okay, let's not waste much of our precious time. We will just do it part by part, where we are going to be looking at obviously vectors in two-dimensional view. So maybe let me do this so that you'll have an idea of where I am. Resolving into components. Okay, diagonal vectors can be broken into components. I think this statement alone, it actually tells a lot. So it is a diagonal vector, nay, that can be broken down into components. Okay, so when vectors are broken into the x and y components, we are determining the horizontal being the x-axis and the vertical being the y-axis effect of the vector. So we can definitely use the sine or cos provided the angle is between the force F and the horizontal. Okay, maybe, let me try to insert a thing there so that I will make use of a sketch to try and explain what could be happening there. Okay, so this is the situation, honorable member, where we definitely have a Cartesian plane having the y-axis. This is the y-axis, and definitely this is the x-axis name. So let's talk about a diagonal vector. Very, very much important, honorable member, when we talk about the diagonal vector. So the line diagonal, it would be something like that. Maybe as we continue, it will definitely make sense as to why we refer to that as a diagonal vector. So if you remember, the statement said diagonal vectors can be broken down into the components, being the x and y components, where we look at the x and y effect of that diagonal vector. So most importantly, it was further stated to say we can use the sine or cos. That is provided that the angle, the angle is between the diagonal force and the horizontal. This is the diagonal force and this is the horizontal. So can you see that angle is between the horizontal and the diagonal force? So if we have that angle formed there, then we can use our knowledge of the sine and the cos. Definitely, honorable member or the member who is honorable, definitely the vertical component, it would be that line which is vertical, meaning being parallel to the y-axis. And when we talk about the horizontal component, it will therefore be that one, which is parallel to the x-axis. Very, very much important on that one, honorable member. But I've just done that for the purpose of explaining the issue of cos and sine. So you might need to be interested to know that we are having a 90-degree angle there. Very, very much important, honorable member. So if we have to resolve this diagonal force into its components, definitely we will need to know what is the horizontal force. That means we are looking at that side, and what will be the vertical force, where we will be looking at that side. You just need to remember that this force, even if it's there, it's still the same as that force which is there. It's the same thing. And then again, same as that one over there. But do not worry that much for now. I'm not necessarily trying to explain the sides of the force and all of that. We just need to know that we are talking about the horizontal and the vertical force. Definitely, we do know very well that when we talk about the cos, of whatever angle should be adjacent, of which the adjacent, it is the x side over the hypotenuse. The hypotenuse in this case, it is that f. So you will see that if we are looking for the x-axis, we will just cross multiply, and then we end up having that force diagonal, or the diagonal force, or the diagonal vector, and then cos of an angle. And then it is going to be obvious that the vertical one will therefore be that one of f sine of an angle, because obviously it is the side which is opposite that angle. So in this way, that's how you would resolve. So very much important. That's why we'll say, we'll refer to this as the what is it, fx, because it is the component. And then this one, it means it would be fy being the component. So this f, it is that one that is attached to cos. I hope that part makes some sense. Okay, then it's fine. Let me go back to that, and then we look at the second part of our notes. Where is that? Oh, I see. I just had to go up there. Why is it not going up? Okay, still saving. Okay, then it's fine. I'll just wait for it to save. And then from there, we are going to continue accordingly. So the knowledge of trigonometry is going to be very much important. Very, very much important. So in other ways, this is all that I was explaining, which is highlighted in gray. Exactly that is what I was explaining, honorable member, or the member who is honorable. Okay, so now, components on a slope. Even though we did not say that one was a component which is not on a slope, but it's fine, worry not. Let's maybe talk about this one, which is a component on a, so let's see, components on a slope. So this is where I am now. What are they saying there? So when forces act on objects on a slope, okay, it is the object which is on a slope, okay. It is useful to resolve vectors into components that are parallel or perpendicular components. The most common force resolved into components on a slope is the weight. Okay. I think I've got an idea of what's happening there. So let's see. It definitely looks like here we are looking at an object which is on a slope. Remember, I'm introducing you to this thing of resolving things into components. So now we are talking about an object, the name. So definitely every object experiences the force by gravity, which is always a force vertically downwards. So this is the G. Very, very much important on that one. So what that statement is saying is that when an object, it is on a slope, what is being resolved into components? It is their weight being forced by gravity. So let's now have a look. It means we will need to form a right-angled triangle based on that. So most importantly, the forces that are going to be resolved, they are in relation to the sloped surface. Name. Let's form a line which is vertical, not vertical, but perpendicular to the slope. So that means a line which is perpendicular, it will have to be that type of a line, because it must form a 90-degree with the slope, isn't it? Otherwise, if we talk about a line which is therefore parallel to that slope, therefore we can do something like that as an example, so that that line, it is indeed parallel to that. So it is two things that we are interested in. The parallel line and the perpendicular line. Why did we have to do that? So that we can form a right-angled triangle there. Once we have formed a right-angled triangle, it becomes very much easy because we have just formed an angle there that we can use in order to resolve the components with reference to that angle between the horizontal and the weight, which is the force that we are going to resolve. Otherwise, it's more like us saying the diagonal vector. Okay, let us now have a look at what's happening there. Definitely, this is the side which is opposite to that angle. It is for that reason why we are therefore going to say this is that side which is FG, and this side it is the one which is parallel to that slope. So this component, it is the one that we are going to say it is equals to our hypotenuse. The hypotenuse in this case, it is that FG. The weight, honorable member, FG and weight is the same thing, name. So that means it is that weight, where you can say W or FG, multiplied by this side is the opposite. So that means it is the one which is sine of an angle. I hope that part makes sense. And then this other side, which is, what is it? The FG component, which is perpendicular to the surface, it is the one which will be equals to that hypotenuse cos of that reference angle. So that's where the formula come from, where now we are having cos and sine being involved. So that's why as we continue, or at a later stage when we look at some forces, you will see that, okay, when you have an object on a slope, you will see that they will say the force component which is acting in that direction, it is FG, name, which is parallel to the surface being multiplied by sine of an angle. And then they will say the component which is perpendicular to the surface. Remember this one, it is parallel to the slope, and that one is perpendicular to the slope. That's why this one perpendicular, it will be that FG which is perpendicular to the slope, and then you move it by cos of an angle. Cos of an angle, because you must just always remember that angle which is formed there. Easy, easy, easy. Is it easy? Maybe easy to understand, but it might be tricky when it comes to the questions. But definitely, you do need to have this understanding on Honorable. Very, very much important. Very, 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 very much important. Trust me when I say, you see that angle there, that angle in a question, it will not be given to you in that position, but it will be given to you there. Just know that it is the same angle. You should not be confused. Okay, then it's fine. I think I did explain that part regarding where this is coming from and all of that. And trust me, honorable member, when I say all that I've explained is coming from my understanding of mathematics. So means you do need the knowledge of mathematics in order for you to be able to have a better understanding of what's happening with the vectors in 2D. Yes, you know, sometimes my English is coming out of the nose. Not the nose. What am I talking about here? See, now I've been thinking too much about making the notes for you, and now, okay, it's coming out of my nose, and that's why sometimes you hear that the foreign accent over worrying. Okay, constructing force triangle. What? Constructing force triangle. Okay, so we are going to be constructing what? The forces in a form of a triangle, something of that nature, honorable member. But trust me when I say, if we do these things part by part, it becomes very easy, very, very easy. It looks like before we can do all of that, there is this statement that we might need to read. Okay, when forces are not collinear, which means they are not a force such that this is a force and then all of a sudden another force extending there and then again another force. So these are the forces which are collinear, if I can put it that way. But the moment you have a force in that direction and then all of a Sunday it's going in that direction, all of a Monday is that, all of a Tuesday. So you see now we are having forces which are not collinear. So force triangles can be used to determine resultant forces or the equilibrium. Okay. So that means with linear forces, if we have this one being 2 Newton, force in newtons, and then maybe this one being 3 Newton, this one being 1 Newton. Then the resultant we can easily say is that maybe combined with that, and then it makes it 6 Newton in that direction. That is the resultant, you see. But the moment they are not collinear, then we have a bit of a tricky situation there, whereby we might need to try and find the resultant, which will not be this easy. Okay, let me just continue that statement where they say, so when forced triangles are formed, basic geometric rules can be used to determine the vectors or the resultant. Okay, I think we will understand it better as we do some examples. Here they're talking about a tail to head. Tail to head. Okay, used for consecutive vectors. Vectors that occur in sequence. Okay, they have given an example there, and this is what they are saying. It is a boat that travels 90 east. You must know where is east, honorable member. You know, in geography, we have this compass where we have north, east, south, and west. If you do not know what west or the direction for the so usenkinken simply means you are in a big trouble. Not big, but you are in trouble, but not just trouble. It will definitely be big trouble. Okay, then it's fine. So a boat travels. Okay, there's a call coming through. I need to squash it. Otherwise, it's going to disturb me. Okay, luckily I managed to do that. Let me just verify if we are still in order this side. Because imagine if that call disturbs this and then now it's no longer sharing or the voices. After having done a very nice intro and now I have to restart and all of that, it might be a bit of an issue. Okay, saving image. I'll just wait for it to save. But okay, it looks like okay. So a boat travels 90 meters east, and then moves 50 north. So this is what has just happened. It travels 90 east. Can you see how long that is? So you can see it traveled longer distance. And then this one, it travels. It is that same boat, remember, that's all remain with the same color. After traveling 90 east, now it goes 50 north. Can you see? So in other words, if we are trying to find the resultant distance or the resultant displace or something of that nature, it's like you watched the boat moving from this point, going to this point, and then from that point going to that point. You have watched it with your eyes doing that. But if you now call me and say, come, the boat has moved. For me, when I look at it, it looks like it just moved from that point to that point. So that would be the resultant if I come after it has shifted from point A to point B and C, whatever the situation might be. So, but for you looking at it, you have looked at it covering vector 1 and then vector 2, and you call me and say, come and see, it is no longer there. Where is it? Is there. So when I look at it, it's like it just went from that point straight to that point. And that single representation of that movement in two directions, it is therefore the resultant. What did we just do? Constructing force triangle. So we've just constructed a triangle, not just triangle, but a right-angled triangle. Very, very much important on that one. Okay, so now they say this principle can also be applied to move. No, this principle can also be applied to more than two vectors taken in order. The resultant is from tail, from the tail of the first vector to the head of the last vector. Okay, now that they are talking about the tail and the head, so that means the tail is from the start, from where it has started, it is the tail. And then it covered that distance, and then from there it ended there. So that means this should be the head. So this would be the tail, and this would be the head. So the head, yes. So that means the resultant, it will therefore from to be from the tail, the start, until the latest point. Okay, so here, the same principle applies. Look at this, honorable member. They are saying it starts from there, from the origin. You see there, you have the y-axis and the x-axis, and that point is the origin. So that means the origin, it is the what? The tail. The boat went there. After going there, it changed direction, and then it went there. From there, it went there. From there, it went there. So you have watched its movement covering vector 1, vector 2, vector 3, vector 4. Then you say, hey, come, cake. Come, cake. Then a come, and you say, that boat, it was there, Mos, when I left. Now that I came back, where is it? It is there. Okay, so that means the resultant, it has just moved from there to there. That's it. Can you see? So with the resultant, we don't waste time. We don't tell the stories and said, no, I went there, then I came back, and then from there, they said, there's no white bread, and then I went to the next Makula there, and then I tried to buy some bread, and then expired wara, and then I had to now go to the other store and all of that, and they said they don't have it, but luckily, I found it there. So for me, I don't want to hear the stories, honorable member. Where did you get the bread? Don't tell me where did you go, what happened, and all of that, and all. No. Where did you get the bread? Okay, from home. This is where I got the bread. So the resultant is like straight to the point, honorable member. We don't wara. No. I hope you get my point on that one, honorable member. So now let's talk about the parallelogram. Okay, parallelogram used for vectors that act concurrently. Concurrently. Would concurrently mean at the same time? Okay, let's just maybe assume concurrently means the same. Okay, used for vectors that act concurrently on the same, okay, at the same time on the same object. Nay, remember parallelogram. So if you don't know what a parallelogram is, then we'll say, okay, the resultant is the diagonal of a parallelogram that originates, most importantly. So we are now talking about the resultant, which is the diagonal of a parallelogram that originates or starts from the tail of the vectors. That is the common origin. Okay, I think this one is straightforward, honorable member, or the member who is honorable. So this is what happens. You have an object there. You see that object there, honorable member. Someone is pulling it in that direction to the right. Another one is pulling it in that direction, vertically upward. So when we talk about a parallelogram now, we are going to construct additional lines which form a parallelogram, whereby you see this one, it is parallel to that. And then we construct another one, which is parallel to vector 2. This is now a parallelogram. So what is the resultant? The resultant is the diagonal. Let me use that, sorry. So the resultant is the diagonal of a parallelogram that originates from the tail of the vectors, from the common point. That's what I meant, which is that one. So that means from that corner, we just draw a diagonal line. In other words, it's like corner to corner. And that becomes the resultant, whereby we have an object there, and then we have vectors pulling concurrently on that same object. Very much important. Okay, so let's look at an example whereby we talk about two tugboats. Two tugboats apply a force of 6,000 Newton and 5,000 Newton at bearings of 60 degrees and 120 degrees, respectively, on a cargo, I almost said boat, cargo ship. Okay, remember, honorable member, doesn't matter whether you call this 60 or 60. At the end of the day, we know that is 6 and 0 degrees. Okay, then it's fine. Let's try and look at that diagram grammatically to say we are having that common point being the origin. So what's happening there? We are having a force of 6,000 Newton in that direction. I hope that part is clear, isn't it? And then again, we are having another one at a bearing of 120 degrees, being 500 Newton, not 500, but 5 tower Newton in that direction. So for us to find the resultant, what do we do, honorable member? We draw those lines which are parallel. So the reason or the main aim is to form a parallelogram. I hope you get that point. So that means we will need a line which is parallel to that other one there. So that is parallel to that. Okay. And then another one which is, nope, it's not coming out nicely there. Let's see, that one parallel to that, just so that this line now it is therefore parallel to. So can you see we've just done a parallelogram, and from there, from that common point, corner to corner, we just do a diagonal line there, honorable member, and then that becomes our a resultant. Easy, easy. Yo, it looks like we are almost done with this one. Okay, manipulasi. What is the manipulasi? The manipulasi as the manipulation. Yes, I think the manipulasi in Afrikaans is manipulation. I'm not sure. You guys can correct me there, but I think because I think everything that ends with shen, then is c. Construction, construction, corrections, correction. I hope I'm right. Okay, manipulasi. So don't be surprised when I say manipulasi on. Okay, so now we are going to talk all about manipulation. What are we manipulating? The vector arrows, or arrows. Okay, the vector arrows can be manipulated to form a force triangle to determine the resultant force. Forces of an equilibrium. Let's just not use heavyweights, man. Equilibrium, what is that? We know there's something called equilibrium, but let's just stick to resultant force. Okay, so the vectors or arrows may only be moved if the magnitude and direction are kept constant. And that is, both of them are kept constant. Okay. You know, sometimes when you study, especially when you study on your own, you just read a statement and same time it doesn't make sense, or you wonder, should I cram this? Or am I supposed to know this? Or what hanan? So just read it and leave it as it is. Just be aware that there's something called the vector arrows, which can be manipulated to form a triangle to determine the resultant force. Then leave it at that. And then the vectors or arrows may only be moved if the magnitude and direction are kept constant, and that is both of them. Okay, so when manipulating the vector arrows, the following has to remain the same. Okay, now you're talking. You see, now you're taking something that can easily be understood. Okay, length of arrows, it has to be the same or constant. That magnitude, the length of the arrow, which refers to the magnitude of the force. So it's like the longer, maybe the distance being long or the force being bigger. Most importantly, angle of the arrow, meaning the direction has to be in the same direction. So you can shift it. It's like if you have a line which is in that angle, but there. Even if you shift it to there, in terms of the length, it has to be the length, the angle has to be the same, and even the direction of the arrow has to be the same. You can't be having from that same line, and then now you represent it like this. Maybe, let me be practical and say, you now represent it like this, and then from there you do that. You are not keeping that the same. You are not manipulating it nicely, because now, first thing first, this arrow is in that direction. Originally, it was like that. You see, the length is no longer the same. This one, you made it shorter. And also the angle, it has changed, because if, for example, we had to measure that angle there, when you compare it with this angle, you can see that that angle there, now it is. So that's what they mean when they say the length has to remain constant or the same. The angle of the arrow again, it has to remain constant, and then the direction of the arrowhead, it also has to remain. You can just shift, but as you shift it to the next position, it shifts with its original properties or something of that nature. Okay, here's an example where they say an object is suspended from a ceiling by two cables. Okay, so below is a free body diagram as well as a force triangle that can be used to calculate the values of tension 1 and tension 2. That T stands for the tension. Would it be the tension, tensy? Would it be the tensy? Okay, let's not complicate it. The tension. Okay, then it's, I think of it, honorable member, as this being the house, and then doesn't matter. Okay, there it is, the house, and then obviously in the house there's definitely going to be a ceiling which has to be flat, and then what is it? All of a sudden there. Let me just I want to do this. See, now I'm trying to move this thing because I've got those notes on my. Okay, then it's fine. Let us say, I don't know why I've got these notes here, but now I'm trying to, I'm trying to move this thing up and down and it's not moving. I don't know why. Okay, then it's fine. I'll just refer to that one there and say, let's see, that ceiling, we are having that and that. I just want to try and diagrammatically explain to you to say, we can say, let's say we have that rope there, and then we have another rope there. They are holding something like maybe a projector there. So here, this rope is experiencing a tension. Maybe we can refer to that as tension 1, and then having a tension 2. Obviously, these ropes are applied at a certain angle. It could be 60 degrees there, it doesn't really matter that much. It could be 45 degrees there, it doesn't really matter that much. But I just wanted you to have a picture to say, that is an object. What did they say in terms of the physics English? An object is suspended, being the projector may be suspended from a ceiling by two cables. You saw those cables most. So now this is a free body diagram as well as a force triangle that can be used in order to calculate tension 1 and tension 2. So that means when we calculate the tensions, we are simply referring to those the force experienced or the pain experienced by the rope, being rope 1 and rope 2. That's why it will be tension 1 and tension 2. Okay. So when coming to drawing a labeled free body diagram, we always make a dot that represents the object name. Definitely, there is that force by the rope and another one by the rope, whereby this one, we will refer to it as tension 1 and then tension 2 because there's a cable there which is keeping that in place. But remember, if you do it like this, it's wrong because you have to also include the arrows to say this rope, they are actually pulling that object in that direction so that it will remain suspended somewhere in the middle of below the soil. It doesn't end there. Every object, honorable member, it has the weight. And we do know very well that the weight in physical sciences we refer to the force of gravity. Very much important on that one, honorable member, or the member who is honorable. So you see now, we've got three forces acting on that object, being the rope, and the weight of that object, which is easily referred to as a force by gravity. So you can say force by gravity or the weight. Listen very carefully, honorable member. Every object has got the weight. Okay, some of them may be weightless. That's why you will see a feather, idling somewhere in the middle of the. It's because it's almost weightless. So that's why it can just float, almost weightless. Not fully, but if there is an extra force like wind, it can easily pull it up. Is it pulling it up or blowing in the air? Yeah, you get it, honorable. I'm sure you're wearing a blazer when you go to school, so you can nicely understand it in that blazer English. Yes. So it's because the mass of that object is very light, and if the mass is light, it will therefore be almost as if it's weightless. Okay. So in terms of a force diagram, not force diagram, but force triangle, it's like we maintain those same forces, but we need to form a triangle. Very much important. You see this line, the honorable member of the opposition party, that line, which is in that direction for the tension number one. It is that same line in that direction. You see now, this one of that rope, it is still that same one, which is in that direction. Arrow the same, angle the same, length the same. That's what they meant when they were saying these things, they have to be kept the same. You can just shift accordingly. And then this one still the same, vertically downwards, having that arrow being downward again, which is our FG or the weight. Can you see? We have just formed a triangle. So that's what it means there when they say a force triangle, whereby you might find that you are having your 90-degree there, which is therefore going to be a right-angled triangle. I was just exaggerating there, honorable man. But otherwise, it's fun. This is all that you need to be aware of. As far as the vectors in 2D are concerned, honorable member, I hope you enjoyed this lesson. Trust me when I say I'm very hopeful that you did enjoy this lesson and have a better understanding of what's happening there. Yes, it was recording, and yes, the screen was sharing. I am happy now. Imagine, just imagine if this recording, the screen was not sharing, and it was not recording, and I've said all of that, and now I still have to say it. Yo.